This is a continuation from part 3. We answered the principal question. Some necessary supplementary questions arose to which answers were provided. It was noted that all the quadratics that were dealt with were such that the coefficient of the square term was 1. In this part, we would conclude by dealing with quadratics where the square term is not unity. We would also deal with some unconventional exercises as revision examples. General expressions. In the case of quadratics where the square term is unity, the general expression of the quadratic is x squared plus kx plus L. The factors are x plus p and x plus q. Since x squared plus kx plus L is equal to x plus p times x plus q, it follows that p plus q is equal to k and pq is equal to L. The general expression of any quadratic is ax squared plus bx plus c, where a, b, c are constants. Example, 2x squared plus 5x plus 3, 3x squared plus 31x plus 80, 6x squared minus x minus 170. Factors they take the form s1x plus r1 and s2x plus r2. Note the difference in factors of quadratics where the square term 1 is unity, the coefficient of x term in all binomial factors is unity. 2 is not unity, coefficient of x term in all binomial factors is not unity. Since ax squared plus bx plus c is equal to s1x plus r1 into s2x plus r2, it follows that a equals s1 into s2, b equals s1 r2 plus s2 r1, and c is equal to r1 and r2. As an example, let us factorize 2x squared plus 5x plus 3. Clearly, 2x squared plus 5x plus 3 is equal to 2 into x squared plus 5 by 2x plus 3 by 2. Now, x squared plus 5 by 2x plus 3 by 2 is of the type x squared plus kx plus L. Can we easily find two fractions such that the sum is 5 by 2 and the product is 3 by 2? The answer is no, but a math wizard can. He would tell you that they are 3 by 2 and 1. Can we try out the completion of squares? In the trinomial, x squared plus 5 by 2x plus 3 by 2, the square of half the coefficient of the x term is added and subtracted as shown. And a difference of two squares, namely x plus 5 by 4 whole thing squared minus 1/4 squared, is made out and is finally factorized to obtain x plus 3 by 2 into x plus 1. Hence the factorization of, therefore, 2x squared plus 5x plus 3 is derived as 2x plus 3 into x plus 1, which is in the form of s1x plus r1 into s2x plus r2. This computation is time consuming. Let the quadratic for factorization be ax squared plus bx plus c. The first instinct is to make it a quadratic where the coefficient of the square term is made unity. Hence, ax squared plus bx plus c is equal to a times x squared plus b over ax plus c over a. As per previous example, using the technique of completing the square is time consuming. The obvious question is there an easy way out? To find an answer, let us go back to the general example where the coefficient of the square term is unity. And as shown below, x squared plus kx plus L is equal to x plus p into x plus q, where p plus q is equal to k and pq is equal to L. Now, let us multiply the two binomials x plus p over a and x plus q over a. Since p plus q equals k and pq equals L, As shown, the multiplication yields the quadratic x squared plus k over a x plus l over a squared. The quadratic trinomial ax squared plus bx plus c to be factorized can be written as a times x squared plus b over a into x plus c over a, and as well as a times a x squared plus b over a into x plus ac divided by a squared as displayed. Compare the highlighted trinomials where coefficient of x squared term is 1, coefficient of other terms are equal if k equals b and l equals ac. Hence, if p and q are such that p plus q equals k equals b and pq equals l equals ac, then as shown, ax squared plus bx plus c is equal to a times x plus p over a into x plus q over a. Pause the video if required. Determining p and q such that p plus q is equal to b and pq is equal to ac is as good as factorizing x squared plus bx plus ac. I call the trinomial x squared plus b into x plus ac as the complement of ax squared plus bx plus c. A rough outline of the factorization of ax squared plus bx plus c is: factorize the quadratic x squared plus bx plus ac equal to x plus p into x plus q. Factors therefore of ax squared plus bx plus c is equal to a times x plus p over a into x plus q over a. Simplify the resulting factors. The ability to factorize at junior school level. If the quadratic was x squared plus kx plus l, we know the three cases depending on the value of k squared minus 4l. Now, in the quadratic, ax squared plus bx plus c, which is identically equal to a times x squared plus b over a into x plus c over a, the corresponding value of k squared minus 4l is delta is equal to b over a whole thing squared minus 4 times c over a. And upon calculation, we get the value b squared minus 4ac over a squared. Delta is a perfect square if b squared minus 4ac is a perfect square. The corresponding value of k squared minus 4l for the complementary quadratic x squared plus bx plus ac 2 is b squared minus 4ac. The test is to find out whether b squared minus 4ac is a perfect square. If so, proceed to factorize. If not, for junior school level, there are no factors with rational numbers. Simple applications 1. Factorize 2x squared plus 5x plus 3. Solution. Compare with the general form ax squared plus bx plus c, which is identically equal to 2x squared plus 5x plus 3. Hence, a equals 2, b equals 5, c equals 3. Therefore, b squared minus 4ac is equal to 25 minus 4 times 2 times 3 is equal to 1, which is a perfect square. Therefore, 2x squared plus 5x plus 3 is factorizable. Then factorize the complementary trinomial x squared plus 5x plus 3 times 2 is equal to x squared plus 5x plus 6. Now, 3 plus 2 is equal to 5 and 3 times 2 equals 6. Using the sum and product method, factorization of x squared plus 5x plus 6 gives x plus 2 into x plus 3. Hence, applying the foregoing, 2x squared plus 5x plus 3 is equal to 2 into x squared plus 5 by 2x plus 3 into 2 divided by 2 into 2. And that is equal to twice. One factor is x plus 2 divided by 2, the other factor is x plus 3 by 2. Upon simplification, we get the factors x plus 1 into 2x plus 3. Simple applications 2. Factorize 3x squared plus 31x plus 80. Solution. Compare with the general form ax squared plus bx plus c, which is identically equal to 3x squared plus 31x plus 80. Hence, a equals 3, b equals 31, and c equals 80. Therefore, b squared minus 4ac is equal to 961 minus 4 times 3 times 80, which is equal to 1, and that is a perfect square. Therefore, 3x squared plus 31x plus 80 is factorizable. Then factorize with the complementary trinomial x squared plus 31x plus 3 into 80, which is equal to x squared plus 31x plus 240. Now, 15 plus 16 is equal to 31, and 15 into 16 is 240. Using the sum and product method, factorization of x squared plus 31x plus 240 gives x plus 15 into x plus 16. Hence, on applying the foregoing, 3x squared plus 31x plus 80 is equal to 3 times x squared plus 31 by 3 into x plus 3 into 80 divided by 3 and 3 into 3. And that is equal to 3 times, one of the factors is x plus 15 by 3 and the other factor is x plus 16 by 3. Upon simplifying, we get x plus 5 into 3x plus 16. Simple applications 3. Factorize 6x squared minus x minus 117. Solution. Compare with the general form ax squared plus bx plus c, which is identically equal to 6x squared minus x minus 117. Hence, a equals 6, b equals minus 1, c equals minus 17. Therefore, b squared minus 4ac equals 1 minus 4 times 6 times minus 117, which is equal to 2809. But 53 times 53 is equal to 2809. Therefore, b squared minus 4ac is a perfect square. Hence, 6x squared minus x minus 117 is factorizable. When factorize the complementary trinomial x squared minus x minus 6 times 117, which is equal to x squared minus x minus 702. Now, minus 27 plus 26 equals minus 1, and minus 27 into 26 is minus 702. Using the sum and product method, factorization of x squared minus x minus 702 is equal to x minus 27 into x plus 26. Hence, on applying the foregoing, 6x squared minus x minus 117 is equal to 6 times x squared minus 1 over 6 into x minus 6 into 117 divided by 6 into 6, which is finally yields, upon simplification, 2x minus 9 into 3x plus 13. The series of videos commenced with the question as to why some quadratics could not be factorized using the standard product and sum technique. The short answer is that the impossibility arises if we confine ourselves to integers and perhaps tolerating rational numbers. A few supplementary questions too were raised, and they were answered. The entire series almost covers all aspects of factorizing quadratic trinomials, and thus the series is concluded. I do hope that you have got to know something which you have never thought much before. If you do appreciate, I am happy, as it bears fruit to my objective. All questions can be mailed to me in the given address. Thank you.